Continue on here with curves. We can use our curves for comparing similar curves. The value in that is that various aspects of the color differences can be separated easily by looking at different portions of the curve and the differences that are present in these key areas. Sometimes it's hard to look at a color visually and see what the difference is. By looking at the curve, sometimes you can get a better idea of where the difference comes from, your formulas. So we can use our curves, the curve of a standard and the curve of a sample, to find small hue differences between them, lightness differences, chroma purity differences, tint strength differences, whether it's cleanliness or dirtiness differences, whether it has metamerism. So some of those things we talked about in the first section, use them for help identifying differences between, generally what you're interested in color matching is trying to match a sample, or you're trying to match a standard, and you make up batches with formulas, and you want to get as close to that original formula as you can so that both colors look the same. That's really what your job is, to make them look the same. So when we use our curves, they're mostly useful when comparing similar curves, such as a standard versus a sample of the same chemical type. So if you have one color you're looking at, and it's made up of one set of colorants, and then your trial is made up a whole different set of colorants, you can't use the curves, compare them too easily. It's not useful when comparing different chemical colorants. But one thing that it can tell you, if that's what you're doing, is that it can show you that there's a difference between them and that you're going to have metamerism present there. Because ideally what you want to do is match the curve so it has the same shape. The only way you can do that is to use the same colorants that are in the standard. Sometimes you can do that. When we work in the lab, we make up standards with our set of colorants, make up unknowns, and then students have to match them. Obviously those come from our colors so that you can get the same colorants. But if you match something from industry, say somebody sends in this Berners can and says, I want this Berners green in a plastic part, you're probably not going to be able to use the same colorants because the printing that goes onto this can probably uses different pigments than what you can use in plastic. You have to use different ones, so you're going to get metamerism, different shaped curves. And if you just look at a single or an absolute curve, it can't give you real specific values on things like strength. You can get an idea what the color is, but not so much of the strength. Most useful application is best practiced by, if you can put both curves on a single sheet of paper and look at them. When we use our spectrophotometers, we can get a printout. It's either on the screen or you can print it on a piece of paper that shows the curves together, and I'll show you some examples of that. Or both curves on a computer screen. Curves of individual batches on overhead transparencies, they can be compared by easily raising and lowering them on, seeing how they match up. We're going to do an exercise where we'll have some unknown mixtures, and we're going to try to figure out which colorants are in it, which pigments, and that's what we'll do. We'll have overhead transparencies, and we can move them to see how well they line up, the shapes. So that's a good way of using these. As I mentioned before, the color or the shade, the hue, determined by the reflection peak of a curve, or the inflection point of a curve. And remember, the inflection point is where it makes a change in direction. So where it goes up, really where it goes up real sharp is what we're interested in when we're talking about hue. So the scale across the bottom of the curve is in wavelengths and nanometers. Visible spectrum from 400 to 700. Certain wavelengths regions will produce a stimulus corresponding to a given color in an observer with normal color vision. So hopefully after all that we've gone through, you understand this part of it. Hue of a spectral curve is usually best interpreted by the position at which the maximum reflection and absorption occurs. Colors generally have either one or two peaks, depending on the color. So if we look at the different colors and the wavelengths that correspond to them, we can see it goes from violet to red. less than 380 is ultraviolet. Infrared, sometimes important. When we were at our conference the other week there's several companies that are coming out with infrared reflective pigments that help for outdoor applications keep the surface cooler. You put it on a roof, for instance, and then it keeps the building cooler and you don't need as much air conditioning. Just think of if you have a black car out in the sun and a white car out in the sun, which one of them is going to get hotter? Black, right? Because it absorbs more of the energy. The white reflects the energy, so when it absorbs, it turns it to heat. And my son likes to watch Mythbusters a lot, and they did a little experiment, and the difference between a black car and a white car was pretty significant. I mean, both got pretty hot in the sun, but there was a pretty significant difference between the two of them. This shows the different wavelengths that correspond to the different colors. Picture of the spectrum there that you're all familiar with. Well, there's certain colors, like I mentioned, that have a single absorption peak. Magenta has an absorption peak, and remember when we say absorption peak, that's the lowest part of the curve, has a peak in the green area, 480 to 560 nanometers. The blue has a absorption peak in the red. Picture of the blue here, so it absorbs here in the red, reflects in the blue. Yellow has an absorption peak in the blue-violet range, and then goes up. Orange goes a little bit farther and goes over. By looking at those curves and where they go up, you can get an idea what the color is. Here's a picture of a theoretical single absorption peak. What color would that be if that was a real color? Green. Green would be opposite. Green would be reflects in the green. See, it absorbs in the green. So what was the color I called it? Magenta. It has a peak in the green area and reflects in the red and blue. So it reflects red and blue, so you get a combination of red and blue. So here's an example we've seen before. Violet. It's a blue shade red colorant. So it's a red colorant. We have red reflected here, and it has also blue, and we have our single absorption peak. Here's red, again with the yellow shade and the blue shade, but it has, again, a single absorption peak. This is less of a blue shade than the other one was, because there's less of a peak over here in the blue part of the spectrum. So how much it goes up in a certain area tells you how strong that color is, or that particular shade is. There's some colors that have two absorption peaks. Green has an absorption peak, or a valley if you prefer, in violet and red. Violet has our absorption peaks in the green and yellow, and gray has peaks all the way across. So this would be, what color would this be? There you go, that's a green. Yeah, so it has our two absorption peaks instead of two reflection peaks. So it's basically the opposite of the one we saw before. And here is a real green colorant. This is phthalo green. That follows that other one fairly closely. All right, the next thing we can talk about is the chroma of the color, or the intensity or purity. All those words are sometimes used interchangeably depending on who you're talking to. Determined by the overall height of the curve, slope or maximum inclination of the curve, the span of the curve from the reflection maximum peak to the absorption minimum peak. We can look at our curves. The purity of a color indicates its chromatic content, or simply how much true color it contains. We judge by the sharpness of the inflection points on the curve. And again, dirty colors spread out, or clean colors go straight up. Phthalocyanine blue, a very steep inflection extending from 8% all the way up to 80%. Very clean and chromatic pigment. Goes up real high. That gives it our clean hue, like we mentioned before. Phthalocyanine blue is great in that it's got a really good color to it, very strong, but there's a downside to a lot of these chromatic colorants is when we use them in the lab, for instance, it takes a hell of a long time to clean them out. They linger and linger. And if you don't clean it out, it can contaminate further batches. We have made up some colorants and some curves, and you get a very distinctive curve when you get phthalo blue contamination. In later classes you'll see this. You can actually use the curves to determine if you have some leftover phthalo blue in there. Okay, phthalo blue is very distinctive. So if you look on the phthalo blue curve, the tail to the right, the shape is a distinguishing mark that helps identify phthalo blue in the mixture. Also note that there's two tails. The GS is the green shade phthalo blue, and the RS is the red shade phthalo blue. Those are the two types that you find in industry. Both of them have a tail. Both of them are very distinctive, but they're different. So that can help you identify which phthalo blue is in your mixture if that's what you're trying to do. Purity, continue. This is a slide of Midori blue. It has an inflection extending nearly over the entire visible region of the spectrum. It is a dirty red shade blue, and it looks like this. Now look at that compared to the phthalo blue we just looked at before, and we see that it's much more spread out, much less pure, and a dirtier pigment than the organic phthalo blue was. We can see that again by looking at the curves and not just at the color itself. Lightness is determined by how high the curve is, and that can be used to calculate the capital Y value, which tells you the lightness also. If you remember back from earlier classes, we calculated tristimulus values, which was the capital Y, and this is the same capital Y value. The average overall percent reflectance of the curve is a measure of its lightness, which is one of the distinguishing descriptions often given to colors, such as light blue and dark green. So when we talk about colors, remember we said that we use three attributes to describe them: hue, chroma, and lightness. This is one way of seeing what the lightness is by looking at the overall height of the curve. Tristimulus value for Y that's calculated is a direct measure of the lightness. Scale goes from 0 to 100. 0 would be a perfect black. 100 would be a perfect white that reflects 100% or all of the light that falls on it. There is no such thing as a perfect white or a perfect black, though. And its value can be estimated from the height of the curve, or you can actually calculate it by finding out the area under that curve for the colorant. So the higher the curve, the lighter the color. The following slide showing 3 letdowns of Midori blue. Curve 1 is the highest of the 3, therefore it is the lightest. Curve 3 is the lowest, therefore it is the darkest. And there we have our 3 curves. Top one is the lightest, the bottom one is the darkest. When we talk about color strength, it can be determined by analyzing the spectrophotometer curve, absorption peaks or valleys. The depth of a color and absorption peak is an indication of color strength when evaluated as a mixture with white. Strength is proportional to the depth of the absorption peak or peaks in the curve. Generally, the wavelength of maximum absorption is chosen as a point to measure the curve's reflectance. And the reflectance values can be converted to K and S values that I mentioned. We can use these K and S values are directly proportionate to colorant strength. K and S values differ from colorant to colorant, so it's best to measure colorant strength between 2 batches of the same colorant type. So if they're 2 different kind of pigments, you can't usually do this. This is a good way of doing an incoming raw material check. And this is done by making up tits of the same ratios and comparing the curves for strength differences. Excellent QC for incoming raw materials. From the curves produced, a spectrophotometer, the reflection values can be converted to K and S values. We talked about those curves in terms of different letdown ratios. We can also talk about them as if they were the same pigment supplied by 2 different suppliers. You can go and buy a given pigment from more than one supplier, just like you can any other commodity. You know, you might be buying one, costs say $1 a pound, and then you get a new salesman comes by, says, well, I can sell you that exact same pigment for 75 cents a pound. Do you buy it? You know, it's the same chemicals, same color index name and everything, you're right. It may not be the same as far as strength. For instance, we could say these are the curves, and this is the one we're using. We can say that's our 90-10 tint, and then we get a sample of the so-called same pigment from our second supplier, and we get this tint. Well, since it's a lot higher than the other one, that tells us that this pigment is not as strong, one that gives us the lower curve. They're the same chemical, so it is, he's not lying to you 100%. It is the same pigment, it's just not as strong. And there's lots of things that can affect how strong it is. That we'll worry about in other classes. The question is, how much stronger is the difference? And there's an actual way of calculating that we'll do in later classes. You can do that by getting the values of these reflectance values generally taken at the lowest point. And then we compare them. They're proportional. You can figure out the strength differences. Metamerism can be identified by using spectral curves between your batch and your standard. There's several types of metamerisms. If you remember, there's illuminant metamerism, observer metamerism, and geometric metamerism. Illuminant has to do with the light sources. The observer, difference between people or instruments. And geometric, which direction you look at the sample. Illuminant metamerism is the most common and really the one we're interested when we're doing color matching. It results when a standard and batch match under one light source, but not under another light source. Happens all the time. This is the result of the spectral curves that have two different shapes. If they don't have the same shape, you will have metamerism. Now the question is that metamerism enough to cause you a problem, or is it close enough where it really doesn't matter? And that really has to be determined by the customer and what the application is. If you're making a product that only goes outside, then you really don't care about artificial light and fluorescent light. You only care about daylight. Observer metamerism refers to a situation where an observer will see a pair of samples as matching and another observer sees them as not matching, even though one illuminant is used. Could be two different shifts at a plant. The day shift person is more picky than the midnight shift QC person. The very same set of samples goes on day shift. He says, no, those are no good. You hang on to it. You don't get rid of it. You give it to the night shift QC person, and they say, oh, yeah, that's close enough. Sound familiar? Yeah. That's due to the differences in color perception between two observers. And that can be difference between two spectrophotometers. Maybe you have two different brands or even two different models or two different units of the same brand and model. They may read differently, just like people can read differently. They're getting a lot better at that, but it's still possible that there's a difference. Or there could be a problem with one of them. Geometric metamerism refers to a situation where the orientation of the sample with respect to the observer affects the apparent color of the sample. If you hold it in one direction, flip it the other direction 90 degrees, then it may look completely different. That's more common in, talk about plastics, in say sheet material or a film material where there's a lot of orientation in one direction. Even bottles, again, if you turn them sideways and put them next to each other, may not look the same because of the orientation of the molecules and how that particular parts are made. Sometimes we refer to that as flop, and a color matcher will put the samples in a color booth and kind of flip them back and forth to see if they both change the same, the flop to be the same. Metameric curves can be recognized easily by the fact that they are generally similar in shape and position, but cross each other a minimum of 2 or 3 times. So crossing of the curves can be an indication of metamerism. You don't want them to cross. Closer the curves are to one another, more likely it will be that they will match under more than one light. So if they're pretty close, you can get away with it. In some cases, you have to match with different colorants because the colorants, like we mentioned with the pop can, aren't the same that you can put in plastics. There's that picture from your book that shows two curves that are similar but are a metameric match because one of them goes straight across and the other one kind of goes up and down. They're both grays, similar grays, match under one light source, don't match under another. If we have a non-metric match, which is what we'd like to have, that's called an invariant match. There's no variation in it whatsoever. A match where the standard and batch match on all light sources can only happen if the spectral curves are the same. And theoretically speaking, only if the material is the same. If we have the same pigments, the same formulation in PVC versus polyethylene, it may not be the same anymore because the material you put it in is different. So the only way the curves can be the same is if the same colorants are used. Spectral curves can be used to determine if the standard and the batch have the same colorants in them, to identify the individual colorants that make up an unknown mixture. If the spectral curves for your standard and batch have the same shape, they both contain the same colorants. If the shapes of the curves are different, they do not have the same colorants. Pretty simple. A couple curves here, a couple examples that show those differences. So here's two curves from our lab spectrophotometer. See, they have the same shape. One's a little higher than the other. That would tell the person analyzing this that those two samples, because they represent two different samples, are made with the same colorants. Now this set of curves here would both be, what color would you say that would be? Now that you're curve experts. You guys are, yeah, bluish green. Would it be very chromatic or not? No, because there's not a big difference between, it's not way up there, it's just kind of flat. But those would probably match more so under artificial light, which has, if you remember the curves from the artificial light, more energy in the red end, less in the blue end, so this wouldn't be magnified very much. If we put it under daylight, since the difference is in the blue side of the spectrum, there's more blue light in the daylight, so that would show up more. One of the biggest uses of curves, and what we'll do an example of here, is that you can look at a curve for an unknown mixture and determine the colorants it was made with by the shape of that particular curve. There are specific parts of the visual curves that carry over into the mixture. So you look at certain parts of the curve that are important for taking the individual curves into the mixture. The absorption peaks are very important parts of the curves. Like I mentioned before, if there's a colorant in your mixture that absorbs the light, it's not available anymore for it to be reflected, so it's essentially taken away from the possibility of being reflected. If a colorant absorbs light at a certain wavelength, not available for the other colors to reflect, so it kind of gets subtracted out. If there's one colorant that reflects at a certain wavelength and one that absorbs there, the absorbing pigment takes precedence over the reflectant one. So therefore, when you were looking at the curves, the lower portions of the curves carry over into the mixtures, not the high parts. Now, the parts of the curves that have a sharp rise or a sharp downturn will show up in the mixture. The wavelength where the inflection point of the curve is important and will also show up in the mixture. So any part where it goes up real fast or comes down fast, that gets transferred, generally gets transferred into the curve for the mixture. When we look at curves, they can move up and down, and we'll take some overheads and do that, move the curve up and down, but they can't move sideways. Where it goes up, what wavelength it goes up, and where those peaks and valleys are, have to stay there. They can't shift it one way or